It's good to be here, and thank you for all coming. Thanks. I try to use my remote controller so that to not block the view of other people, but this guy always breaks down during important talks, so forgive me if it happens again. So this is, I'm going to talk about resource allocation in OFDM systems, and this is a joint work with many of my colleagues, including my former advisor at Northwestern University, Randall Barry, my colleague, and current mentor at Princeton, Professor Meng Chang, and also colleagues from Motorola, Vijay Subramanian, Rajiv Agro, and also other colleagues from Hong Kong, Rafael Sangela from Belgium, Mark Moven. So the sponsors for the talk today is from NSF, Motorola, and Noctair. Oops. The complaint is staying too long. OK, good. So what is OFDM system anyway? So OFDM system is a technology that divides the whole frequency band into a couple of parallel orthogonal carriers or channels or subchannels. Depends on what kind of system you're talking about. So the major benefit of using OFDM system is that it can offer high spectral efficiency, eliminate intersymbol interference due to multipass fading in the wireless channel. So the OFDM has been the basic technology for many communication standards, including WIMAX, which is based on 802.16, and also Wi-Fi, which is the A and G version of the .11, and also in the wireline network, for example, DSL. So in today's talk, I'm going to focus on two kinds of resource allocation problems. The first is OFDM. Let me stand this way so that you can see that. The first is OFDMA system, where it's orthogonal frequency division multiple access standard, which basically here that everybody is assigned a subset of the total carriers in the system. And assuming we are only looking at a single base station, single cell case, then there's no interference among users. And the resource allocation there is to determine the user-carrier association. So how you can allocate user to the carriers, and also the corresponding power allocation on these carriers. And the second is interference-limited OFDM system, as I call it, where everybody has the freedom to transmit over all the carriers in the system. And because of this, there's interference among active users on the same tone, on the same carrier. And the problem there is to determine the power allocation across users on the tones to mitigate interference. So I'm going to talk about the three applications in this talk. The first is the schedule and resource allocation in WIMAX networks, which is based on the OFDMA technology, where there's no interference among users. And the second one is a power control in multi-channel wireless ad hoc networks, where there is interference among users. And the third one also is interference-limited OFDM system, which is motivated from the spectral management in the DSL networks. So here's a quick summary of the three models I'm going to talk about. So the first model is motivated by a WIMAX technology, which is an infrastructure-based network, a wireless network, and there's no interference. And objective is design optimal scheduling and power allocation. So the second network is a wireless ad hoc network. There's no infrastructure, and there are interferences among users. And objective is design optimal power allocation. And third one is a DSL network, which is an infrastructure-based wireline network. And there are, again, interference among users. And objective is again, power allocation. So here is the list of major references related to today's talk. And there are more information and publication can be found on my webpage at Princeton University. So first, WIMAX network. So what is WIMAX network? WIMAX is a suite of products based on the 802.16 standard, which provide metropolitan area network broadband access connectivity. And theoretically, it can cover a distance, a single base station in the WIMAX network can cover a distance up to 5 kilometers and provide a shared data speed up to 70 megabps. So this is really a broadband network. Can use the frequency from 2 gigahertz to 66 gigahertz, a subset of that. And different from the usual wireless LAN, 802.11, here is that the WIMAX defines a scheduling-based MAC protocol. So it's a centralized system. So here we consider joint scheduling and power allocation in a WIMAX network, where we consider a downlink transmission with channel-aware scheduling. So essentially that each time slot, each scheduled interval, that's the scheduler at the base station will take into account of the channel conditions of the users and try to schedule which user to transmit. And within the time slot, it's using OFDMA to multiplex across users. And many of these existing channel-aware scheduling algorithms can be thought as gradient-based scheduling. So what do we mean by that? Essentially, we can assign each user a utility function, which depends, for example, on the throughput or delay. And then the scheduler tries to choose a rate vector across all users from the rate region, which is a function of the channel state E, to solve the following problem. To maximize the product of the gradient of the utility, which has one element per user, dot product to the user's rate. So as we can see that this is actually a myopic scheduling policy because it requires no knowledge of the channel statistics or the arrival traffic statistic, only focus on the current channel. And depends on the utility you assign, it could be corresponding to different kinds of allocations, proportional fare, maximum rate, stabilizing policy, for example. So here that I only consider this generic form and see how to solve this problem in the OFDMA setting. So as we say that in the scheduling problem that we have to choose a rate from the rate region. So the first problem is how to characterize the rate region, right? So here is which region like for the OFDMA system. So this is the vector of all users. This is the rate of user I, corresponding to the achievable rate from all the carriers that is allocated to this particular user. Here the variable xij is the time fraction of the carrier or tone j allocated to user I. The pij is the transmission power allocated to user I on tone j. And eij is a parameter here, which represents the received signal-to-noise ratio per unit power, which represent the channel condition in the current scheduling time slot. So the rate is summation of the rate across all users depends on the power, channel, and the time fraction, and also has to lie in the feedable region, where this feedable region is characterized as the following. First of all, these two variables, channel allocation and power, should be non-negative. And also, very importantly, in practical OFDM system, that each channel is only allowed to allocate to one user or no user at all, which means the xij should be either 0 or 1. This is an integer constraint, which is difficult because it makes the problem defined later a non-convex problem. And the second is that the summation of the xij over all user I on a particular tone j should be less than 1, which essentially, as I said, either assigned to one user or no user at all. And because this is a downlink transmission, so the transmission power allocated to all users or all tones should be less than the total power constraint at the base station.
So why doesn't the power constraint have an xij times the pij? Since it sounds like, it looks like in there you're counting the
right.
power that is transmitted.
So essentially, later we'll realize that the optimal pij is a function of the xij. When xij equals 0, then corresponding pij equals 0. So that's where deal with the problem you mentioned. Yeah.
And is it, when you said the xij, clearly the integer xij is a very hard constraint. And why not just allow those to vary between 0 and 1 smoothly?
Right. So I should say that. So this is basically this problem is motivated by the research at Motorola for their next generation WIMAX product. And they're in the practical system that once you decide a scheduled interval, and actually it's defined a standard as well, that you want the particular scheduling interval, the tones should be allocated to just one user, a particular tone. You don't want to timeshare because it adds complexity. So theoretically, actually later we'll relax this constraint. But later on we realized that by relaxing this constraint, really, in most cases, the optimal solution will automatically satisfy the integer constraint. So this is the problem that we want to solve, the joint scheduling resource allocation problem that has to be solved at every scheduled interval at base station. So we want to choose the channel allocation and power to maximize this primal variable, which is essentially the aggregated rate across all users. And the weight factor Wi represents the gradient of the utility, as I mentioned before. So what's the technical challenge of solving this problem? The first technical challenge is the integer constraints. And the second is that because this has to be solved at every scheduled interval, typically it's on the order of millisecond. So we need to find an algorithm that is really low complexity and fast convergence to solve it.
So what's the motivation to for the weight xij log and 1 plus some xij in the denominator?
Mm-hmm. So why use this form, right? So if you consider, just to consider integer constraint, there are really many forms of formulating it, right? Essentially, you only have 0 or 1, right? So here, this will essentially leading to the next slide, basically that after you relax this, this becomes a convex problem, convex formulation. And also, it also has physical meanings. Essentially, it says that if this is the power allocated to it, this is time fraction, for example, 0.5. So half of the time you are using this tone. Then essentially, at the active part, you are transmitting at twice SNR, right? And then this is the rate you can achieve, instantaneous rate, and times the fraction you get. So this is indeed if you allow time fraction.
No, the time fraction of power you are using is xij pij, right? By pij by xij.
So pij is allocated power, the total power allocated to you for this time slot. Then if you're only using half of the time, they can use twice the peak power during the active time.
I think it's just a dimension. Previously, we had like W log of 1 plus something by W.
Mm-hmm.
So it's just how much.
Average power constraint.
pij is the average power allocated.
Spread over all dimensions.
That's right. Yeah, pij is the average power. Yes, it's not instantaneous power. So this is the problem we want to solve. And actually, to reduce the complexity, we first consider a relaxed problem where the objective function is the same. However, we changed the feasible region by relaxing this integer constraint into a continuous constraint. And then we can show that this is called problem 1b, previous called problem 1a. And later we'll show that typically the optimal solution of this relaxed problem is also optimal for the original integer constraint problem, which means the optimal solution satisfies the integer constraints. And occasionally, it's not a case, then we can find a near optimal solution of the original integer programming problem with almost no additional complexity. Now, I'll explain what that means. So let's first solve the relaxed problem. And as we said, that by this formulation, it's a convex problem, and it satisfies the Slater's condition. So there's no duality gap. We can use in the usual story, the dual algorithm to solve it. So consider the Lagrangian by relaxing the total power constraint and the time allocation constraint per tone, right? And we can optimize this Lagrangian over time allocation x, transmission power p, and the dual variable associated with x. And after optimizing over these three variables, we can actually get closed form solution of the function in the scalar lambda only. And this is also specific for this problem. In general, you may get some numerical solutions, do some numerical search. But here we get closed form. Right? And because this is a dual function, it is convex, then we can find the optimal lambda by one-dimensional iterative search. So you can pick your favorite search method, for example, the bisection search, golden section search, right? Because it's one-dimensional, very low complexity. So after finding the optimal dual values, we want to look at what kind of primal values we get. And these correspond to the things we are interested in. How to allocate the power, how to allocate the carriers, right? And after solving this, essentially, this leads to the following result. And this is an interesting structure because essentially the mu ij is a function calculated on each user on each tone, which is a function of the dual variable lambda only. And essentially, we are doing a simple sort of user per tone, that we are sort the user I, sort through all the users on a particular tone j, and look at what's the maximum value. And if the corresponding value of a particular user equals this maximum value, we assign this channel to him. If not, we assign 0. So this naturally becomes an integer solution. Right?
Did you say what mu ij is yet?
I didn't say that. It's embedded in this sentence, find a closed form solution. Yeah. It's actually a pretty complex but closed form solution. Yeah. So in most cases, which is verified by the simulation, that actually no tie occurs on any of the tone G, which means that on each tone, there's only one user achieve this maximum. Then that automatically satisfies the feasible constraint in the integer programming, in the integer problem, right? And this gives us the optimal solution of the original problem.
So
However,
one guess for when you can get probabilistically two users have the same channel, right?
Mm-hmm, mm-hmm. Typically, there are two users. Yeah, there could be multiple users as well. But the problem. Yeah. That's right.
Would that happen?
That would happen. Yeah, that would happen. The reason is that because remember the original definition. Essentially, at each time interval, you are solving optimization problem with the fixed weight Wi corresponding to the utility, gradient of the utility. And once you do the optimization later, next time slot, the user with not allocated enough rate will increase the Wi. Well, basically, they increase their priority. And later on that, you have to schedule that user. And that MA ends up to be scheduling two users at the same time. It might be something that you want to do. However, that is not allowed in a practical system. So we have to break the tie and pick one user at a time. So when tie occurs, that essentially multiple users achieve the maximum on a tone J, which means the corresponding result will be multiple users per tone, not prime feasible, right? And then we need to break the tie to find one user per tone to satisfy the practical constraint. So breaking the tie is essentially choosing one user per tone. Essentially corresponds to choosing one power allocation, because given the channel allocation, you can calculate in closed form what will be the corresponding power allocation, which is essentially a linear function in the channel allocation. And actually, this motivates us to utilize the subgradient information of the dual function, which is the residual power here. It's the total power constraint minus the total power allocated to all the users. So this information is obtained at free, right? Because you already calculated the optimal lambda, and you can look at all the ties and calculate this directly. Then we can choose the smallest non-negative subgradient, which is just one way of breaking the ties, right? And this will determine a feasible channel allocation. However, after doing this channel allocation, x is fixed. Then we look at the power p, which is another variable we want to solve. And the resulting power constraint might not be tight because you are picking a smallest non-negative, which might be positive, right? So this term is positive, which means p is not fully utilized. And in that case, you will re-optimize the power allocation across all users, given the channel allocation. And that is essentially equivalent to solving a single user water filling problem, which is very simple. And actually, the optimal solution can be found in finite steps. So all these things, although look complex, adds little complexity to the algorithm. So here is the summary of the algorithm, which we call SRT algorithm, scheduling and resource allocation with tie breaking. Right? Essentially, first we consider relax problem and solve the dual function in closed form by optimizing over xp and mu. And you do the one-dimensional search to find the optimal lambda. And you solve for the primal variable. If no tie occurs, bingo, you're done. Right? Then you can stop the algorithm. And if tie occurs, you can break the tie using the subgradient information and re-optimize the power allocation in finite iterations, which consider the iterative search here. These steps have little complexity.
So can you somehow go back to the description of the solution here now with the mu ij?
Mm-hmm.
So if you have just one user in the system, right? I would think the solution has to go back to single user water filling because you have an average.
That's right. That's right. Yeah.
And somehow is that what happens here with like somehow there'll be tones that simply go unused? Is that?
You mean in the single user case?
Well, yeah, in the single user case, and presumably in like you have a multi-user case, but where the powers are tightly constrained, where channels that are bad for everybody go unused. So all the xij's for that channel for all users might be zero based on
right. So precisely, actually, here when this guy achieves maximum, any value between 0 and 1 would be due optimal. So in the single user case, because in the multiple user case, when there are enough users, there's always one user has a good channel quality at one particular carrier. So you want to allocate one user to that. But in a single user case, that essentially there's only one magic, sorting all through one user. So always this case. And this guy, this value should be 0 to 1. And any value is feasible and due optimal.
And there's no simple description of the uij.
That's right.
Someone has to involve the eij.
Yeah, that's right. Exactly. Yeah. There's I don't have slides here. Essentially, it depends on the W you have. It's product of the coefficient Wi, which is the gradient of the of the utility times the channel condition over a Lagrange multiplier. So it's actually a water-fitting kind of solution.
Oh,
Yeah,
okay.
yeah.
So it is simple.
Yeah. Where, I mean, there is some catch.
Relatively. I mean,
Yeah.
in some known parameters expressed.
That's right. That's right. Yes. 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 Yes.
So you said WI is a gradient of the utility function?
WI is a gradient of the utility function, and it's a fixed parameter at this kind of time scheduling interval. And it can change from interval to interval because the utility function change based on what kind of rate you allocate to a particular user.
And so what is it, do you have situations in DSL systems where there's more than one user?
Yeah. It's a one.
I'm a wireless guy. I don't know anything about DSL.
In the DSL case, which is the third scenario I'm going to talk about, in that case, everybody can transmit on every tone. So the problem is not on breaking the ties, shooting one user. It's indeed that everybody is transmitting on a particular tone, and you want to mitigate interference. But here that we want to, in a practical system, we want to allocate only one user per tone. So it becomes this little bit difficult problem. I mean, difficult in the sense it's integer program, but simple in the sense there is no interference.
So here if one user had in one tone, you transmit the user with the best channel. Was the best channel in that tone?
One user on per tone, and
That user is the user who has the best channel among the set of users. Who are
typically, however, it only depends on the WI, right? If a user has bad channel, but it has a very high WI, it has high priority, so you may want to also schedule that. Yeah, that's right. Yeah, I already explained the DSL, which is a little bit different scenario and a more interesting scenario later. To put more interesting stuff in the later part of the talk to keep people awake. Okay, so here's the simulation result. Essentially, we consider a cell of 40 users and bandwidth 5 megahertz. And we'll consider the well-known alpha fair utility with a utility parameter 0.5. And here we consider 4 algorithms. First, we call 4 algorithm. It's essentially the scheduling resource allocation with tie-breaking algorithm. The other are 3 heuristic we propose. Right? And this is the user throughput CDF. So as we can see, this blue curve is the SRT algorithm. And there's another blue dotted curve overlapping with this. It's another heuristic, which achieves almost optimal performance. And these are 2 other heuristics, which leads to a little bit unfair allocation because the rate is more spread out. However, if you look at the utility, it achieves above 90%. So reasonably well. And the total throughput achieved around 20 megabps per cell. Okay, so this is the summary of the first part, that we consider mixed integer and convex optimization for joint scheduling and resource allocation in WIMAX network. We design an algorithm that achieves optimal solution where there are no ties with low complexity. And when tie occurs, we break the tie, which just adds little complexity. And we also propose simple heuristic, which I don't have time to illustrate the details, which performance closer to the SRT algorithm. What is not covered here is that we also consider putting more realistic constraints, for example, limiting the maximum SNR per user per tone because of limited choice of modulation coding schemes. And that will make the function mu-ig a little bit more complex. However, it's still in closed form.
So your heuristic algorithm is also centralized?
It's centralized. Everything is centralized. Yes. Yes. Because you require, essentially, all the heuristics require sort across all users. And nobody can do the sort by himself. Only base station collect information and do the sort. Yeah. And I also consider a different channelization method, which if there are 512 tones, we can group into a smaller number of tones to reduce the channel feedback overhead. Okay. So here goes to the second application, which is different. It's an interference-limited case where there are interference among users. And this is a model of the wireless ad hoc network with multi-channels. And I guess I don't need motivations for this sensor or ad hoc network in WINLAB. So I'll go directly into the details. So the ad hoc network with no fixed infrastructure or centralized controller. Right? And there are M users, which each user is considered as a transmitter-receiver pair. So here, T1 is the transmitter of user 1. R1 is the receiver of user 1. So this is considered to be one user, okay? And there are k parallel channels. Here are plotting like 2 parallel channels, for example, right? And because the freedom, everybody can transmit in every channel, every carrier. So there are interference, right? So this T1 guy is transmitting useful signal here, but generating interference to the receiver of user 2, receiver of user 3, right? So this is the basic model. So the goal here is to design distributed power control algorithm to maximize the network utility. So to simplify the problem and gain intuition, first let's consider a simple problem where there's only a single channel in the network. So there are still interference, but a single channel. And we'll see how we deal with this problem. And later we'll put back to the multi-channel inside. Right? So the problem is to maximize the total network utility, where each user has a utility function, which is increasing and strictly concave in the signal to interference plus noise ratio, which is in this form. Right? This is the transmission power of user n. This is the channel gain between user n's transmitter, user n's receiver. This is the background noise. The PM is the transmission power of an interfering neighbor, user m. This is the channel gain from user m's transmitter to user n's receiver. Basically, it's the interference channel. Right? And we want to maximize this total utility such that the constraint is that everybody can choose a transmission power between minimal constraint and maximum constraint. Right? So what is the challenge of solving this problem? So first, this problem is highly coupled across users due to the interference here. Right? And also, because of the interference, although the utility is concave in the SNR, it could be highly non-convex in power. And our objective, because it's an ad hoc network, we want to design distributed low-complexity algorithm with fast convergence and optimal performance, which seems to be impossible in the general case. And we will later show that under certain conditions of utility functions, this is indeed possible. So next, I'm going to first explain an algorithm that we propose, a distributed pricing algorithm. And later, we will show the convergence performance of this algorithm and how it solves this problem. So this is the algorithm we propose. It's called ADP algorithm, Asynchronous Distributed Pricing Algorithm. So there are 2 phases in this algorithm. First phase is price announcing phase, that each user n in the network announces a price per unit interference, which is calculated as the derivative of the utility function in terms of the total interference it receives. This represents the sensitivity of the utility function in terms of current interference level, and always positive. Right? And we can do some simplification and realize this price information can be calculated by knowing the utility function, the current SINR, the transmission power, and the channel gain between the user's transmitter and receiver. Everything is local information. So which means this price can be calculated locally. Then in the second phase, power updating phase, after everybody calculating all the price and broadcast to the network, then the user n would update its transmission power to maximize the surplus, which is defined by the utility function, difference of the utility function and the payment to the network. This payment is a product of the transmission power and a weighted sum of the prices from other users. So this is the price announced by user m. This weight is the transmission, is the channel gain from user n's transmitter to user m's receiver. So this essentially says that how much this guy is interfering with other users. Right? So choosing a power to balance the utility you get and interference generated into the network. So this is the key idea. And then the users repeat these 2 phases asynchronously across themselves. They don't have to announce the price or update the power at the same time. You can do whatever they want. And this is a scalable and distributed algorithm because everybody need to only announce a single scalar price to the network in this single carrier case. And they only need to know adjacent channel gains, HMN here, to calculate the payoff function, which doesn't require the global information of the crosstalk in the network.
So you're assuming your interference is sort of limited in certain range of distances. Everybody could potentially interfere with everybody else.
That's right. That's the assumption here. Everybody is interfering with everybody.
When you say adjacent channel,
adjacent channel, which means that this.
you mean the people who are adjacent, right? There's only one channel.
Right. The adjacent channel, which means that the channel again that has some physical connection to your transmitter. Right. So you don't care about the channel between other users. So that's what I mean, adjacent channel.
So what is pi m in that?
Pi is the price you announce. So here, pi here and pi here, the price you announce by a certain user.
So the user has to know the prices, like this is, like that iteration, the power update is by user n.
Right.
You know, in principle, all the other prices.
All the other prices in the network.
And
That's
he has
right.
to know the gains of those users to his receive it.
Right, right.
And your view is, oh, practically you just ignore the very small values.
Yes, yes. There's no slides here, but we had a paper in Miracon where we explicitly studied the effect where you only consider the price within a certain range. And with the shrinking of the range, the performance degrades. However, the degradation is very graceful. So you only need to know really a couple of users around you. That's enough. Yeah. But in this talk, I'm considering everybody knows all the prices, and which enable us to achieve global optimal solution in some cases. So this is the algorithm that we proposed. So let's think more about what this algorithm means, right? So there's actually an interesting interpretation of the prices in this algorithm, which correspond to the Pigovian taxation in microeconomics. And Pigot is a well-known economist that he proposed this kind of tax for users who generate negative externality in the society. For example, people generate pollution, right? People smoking, right? So for these people, you have to pay tax for your bad behavior. And here in our communication system, the bad behavior is interference. So you have to pay tax. And the way to calculate the Pigovian tax is exactly the same way as calculates the price here. Okay? And in economics, Pigovian tax typically lead to social optimal solutions. At least that's the goal of this taxation. So our ADP algorithm is essentially a distributed process of discovery of the Pigovian tax. So the question we want to answer is that whether this algorithm converge. And if it converges, what does it converge to? Especially where to maximize the total network utility. And the last but not least question is that how fast does it converge? So first, let's look at the convergence property. And the short answer is that convergence depends on the utility functions. Right? And to characterize the particular class of utility functions, we define the following term: the coefficient of relative risk aversion of a utility function, which is defined by the SNR times the second order derivative or the first order derivative. And this is, again, not a new term. This is a term we're defining microeconomics. And this basically illustrates how concave the utility is. Then we have the following convergence result. If for everybody they have a positive minimum power constraint, could be arbitrarily small. And if the coefficient of relative risk aversion lies in the range between 1 and 2 for all feasible values of SI and R, then there's a unique optimal solution. Oops, there are two optimal here. There's a unique optimal solution of the problem 2A, which is the single carrier case. And ADP algorithm globally converges to that. So for example, this condition B is satisfied by the log utility always. And the proof of this result is based on relating this ADP algorithm to a fictitious supermodular game, which, as I promised. So here there are three entities in this case. There's a problem that network utility maximization that we want to solve. There's ADP algorithm that we propose. And there's a fictitious game that we constructed in terms of proof. So what are the relationships between these three entities? So first we can show that the KKT points of this problem corresponds actually to the fixed points of this algorithm, which by construction correspond to Nash equilibrium of this game. And then we can also show that the price power updates of this ADP algorithm actually correspond to the best response updates of this fictitious game by properly choosing the payoff function in the game.
What does the best response mean?
So in a game, that the best response means that if a user considers the strategy of all other users are fixed, then you choose his strategy to maximize his payoff. Then the fixed point of the best response is the Nash equilibrium. Yeah, so that's the relationship. So then here is the first sub of results, which is not related to our theorem, but it's actually more powerful. In the general case, when this problem could be non-convex in the power, then there could be multiple KKT points. And that corresponds to multiple fixed points by definition, right? Because of this relationship, which correspond to multiple Nash equilibrium. And more importantly, if we can show this game is supermodular, then that will show us that by starting from some particular initialization, the best response would converge to a certain point of the Nash equilibrium, which you know beforehand. And this will translate into the conditional convergence of the ADP algorithm. And this result is just general. Whether the problem is convex or not, this applies. And now this is related to our theorem. If we are very lucky that have one unique optimal solution of this problem, that corresponds to the unique fixed point of this algorithm and the unique Nash equilibrium of this game. And the supermodularity of this game guarantees the global convergence of the best response to this unique Nash equilibrium, and also asynchronous across users, which proves the global convergence of this ADP algorithm. So in order to show this relationship and utilize this graph, what we need to show is the two. First, we need to show that there's a game which is supermodular. And the second, we need to show that there's a unique optimal solution of the original problem. Then we can prove the theorem. The first is some background on the supermodular game. Supermodular game actually is very common in economics. It's essentially a class of game with strategic complementaries, strategic complementaries. And a sufficient condition which is useful in a single channel case is that if the strategy sets of the users are compact subsets of the real line, and everybody's payoff function Sn has increasing differences, which has a positive cross difference in terms of his strategy and other people's strategy, then this is supermodular. And key property of a supermodular game is the following. So first, a Nash equilibrium exists. So you automatically get a Nash equilibrium, maybe more than one. And the second, if the Nash equilibrium is unique, then the asynchronous best response update will globally converges to that. So this is very powerful convergence result. So how to use the result in our case? Well, first we have to construct a fictitious game. The way we do that is that we split each user in the Hoc network into two fictitious players in the game. Then we will choose the player's payoff function such that best response updates correspond to the power price updates. So this is by construction. And then if you look at the original condition in a theorem, that this condition on the coefficient of relative risk aversion guarantees two things. The first, this game is supermodular after proper strategy transformations. And the second, this problem has a strictly concave objective function on the log change of power variables. And also a compact compact feasible set, which means there's a unique global optimal solution corresponding to unique fixed point and fixed unique Nash equilibrium. And the global convergence can be proved.
So somehow, like, each fictitious user has a best response update. And
Yes.
A combination of two fictitious users' best responses
Right.
correspond to a power price update.
Right. So each user in the network update power and price. And they update it in a cooperative fashion because they are announcing price exactly according to the derivative. They are not arbitrarily announce the price to maximize the surplus. So the original network is a cooperative fashion. It's not a game. And in this game, we split into two fictitious players. One updates the price, one updates the power. Now, by constructing the appropriate payoff for these players, we make sure that when they do the best response, they are actually updating power and price in the same way that we are doing in the ADP algorithm. So that's the relationship between these two. Yes?
So first of all, this problem between NC is multiple carriers.
Multiple carriers, yeah. Oh, yeah, sorry. Yeah, this is SC, yeah.
Oh, it is SC.
This is SC, yeah. Later we have result for MC as well.
Okay, and also
Thanks a
when
lot.
you said the change of variable, did you mean powers as a variable or is
Power as a variable. So original power as a variable. Then you have defined, for example, pi, right? And you define a yi equals log of pi. And the utility function is jointly concave in the yi. So this is a nonlinear transformation. This is a trick used in the geometric programming. Yeah.
I mean, same question on that. You had 1 plus SNR in the logarithm, right?
That's
1
right.
Plus SNR. So,
Yeah.
and from what I know of these papers, typically the transformation when you make this log transformation, because of 1 plus factor, normally run into trouble when you
Yes.
approximate SNR to be very large.
Yes,
Is that
that's
all hidden in this?
that's a good observation. But remember, there's a catch here that utility function we define is on the function of the SNR, not on the rate. So it's not necessary that 1 shows up here.
Okay.
Yeah. And in that case, it's indeed non-convex. And we can use this result to show the convergence where there are multiple KKT points. Yeah. But I'm choosing to say this result because it's nicer. Yeah. Okay. So far we have answered the question whether this algorithm will converge, and when it will converge, and whether it will converge to the optimal solution. The last question is what's the convergence speed? Right? So here we compare the convergence speed of ADP algorithm in terms of power and price with another algorithm, gradient-based algorithm, which is based on Meng Chang's JSAC 2005 paper, where they consider a joint congestion control and a power control. So this is only comparison of the power control part. We have no congestion control here because we consider single hop transmission. So everybody has log utility. There are 10 users. So remember that in the ADP algorithm, when you update the price, you calculate the derivative. When you update the power, you just maximize the surplus, right? So there's no step size involved. Because of that, the ADP algorithm converges much faster than a gradient-based algorithm, where you have to keep a very small to guarantee the convergence, which is typically the case in many iterative algorithms. Right? So in fact, if in practice everybody has a finite choice of transmission power, right, which is always the case, then we can actually write out a finite upper bound of the number of iterations below which the algorithm always converge. So let's return to the multi-carrier case, multi-channel case, which is what we're really interested, right? And in this case, we maximize total utility, where the second summation is essentially the utility of user n, which is the summation of the utility across all carriers. And the received SNR is in this form, which similar as the single carrier case, but with a superscript k. Right? And the power constraint is a little bit different. It's a little bit different because you have a total power constraint across all channels. Okay. So this is the only difference. So we can modify the ADP algorithm for this multi-channel case. In this case, we have two classes of classes. The first class, user n still announce an interference price pi n k on each channel k, where you have a total k channels, you have a total k interference price. Same thing represents the Pavlovian tax on this channel. And the second, user n also keeps a local resource price, not announcing to the network, just keep local to himself, a scalar mu m, which reflects the power constraint. Right? So this is essentially a dual decomposition. Try to enforce the power constraint. This is the dual variable, mu m. But this pi is not a dual variable. So in the primary updates, there are two power updates and interference price updates. The primary update is separable across channels. Essentially, user n will choose the transmission power in a particular channel to maximize the surplus, which is the difference of the utility in this channel and the payment in this channel. And the payment is not only determined by the interference price announced by other users, but also determined by the resource price you kept to yourself. And then the interference price is updated as in a single channel case by looking at the sensitivity. Right? And in the second part, the dual iteration, where users update the resource price mu n, a scalar, according to the subgradient, which essentially look at the degree of violation of the total power constraint, and use a fixed constant step size kappa, the same for all users to update this. Right? So what is the convergence results of this more complicated algorithm? So what we can show that this dual ADP algorithm globally and geometrically converges to the unique optimal solution of the problem, multi-carrier problem, under similar conditions of utility function in the single channel case. And also with a small enough constant step size kappa. So this is there's a lengthy proof for the theorem, essentially that to show the geometric convergence, we need to show the strong convexity of the gradient of the dual function. And I also need to show the Lipschitz condition for this constant step size. And more importantly, we need a separation of timescale assumption, which means that the primary updates will instantaneously converge between any two dual iterations. However, we show that this prime updates converges really fast. So this might not be a severe limitation. And we can see in this particular numerical example that indeed, in practice, we do not need the separation of timescale. So here we consider a network with 16 channels, 50 users. Everybody has log utility. Here is the total number of prime updates. Here is the relative difference of the utility function in terms of the current what you achieve and the final what you converge to. So here we try 4 different algorithms. Ideally, we need we should allow infinite number of primary updates between any 2 due iterations to let it converge first. Right? However, here we're limited number of primary updates from 1, 3, 5, 7. As you can see, the convergence speed is really not that different. Right? So this shows that in practice, the dual ADP algorithm is very robust to the implementation details. Right? You can choose the updates according to whatever you want, and it won't change the performance a lot. So here's the summary of the second part. In this part, we consider power control in a multi-channel wireless ad hoc network, where we proposed a dual-based ADP algorithm that could achieve optimal solution with fast convergence on the proper conditions of the utility functions. And the price announced in this algorithm corresponds to the Pigovian text in economics. And what is not covered in this talk is that we also consider primary-based ADP to solve both convex and non-convex multi-channel power control problem, which needs a little bit more work, but has more limited result. And we'll also consider the convergence of the ADP algorithm where there are multiple channels. For example, in a spectral sharing environment, there are multiple vacant channels to choose. But due to technology reason, each device can only transmit on one channel. So in that case, how the ADP will perform and whether it will converge or not. So let's go on to the third part, which is the most interesting part from my point of view, because it's a completely different story. It's a wireline network. And there's a very interesting structure of the problem that we can exploit to do something that is just impossible in the wireless case. So in this case, we consider the optimization of the power in the DSL network, the digital subscriber line. So a short history. That the DSL network basically used the traditional telephone lines to transmit data, right? And it is in the early 90s by John Chioffi that he introduced a so-called discrete multi-tone standard, which is another variation of the OFDM standard, that converts the original telephone line, which can only transmit voice, into a broadband media. So how can they do that? Basically, that this is the frequency band, for example, for the offered by the copper line, the telephone line. And the original voice transmission only uses a very low frequency band and smaller than 3.4 kilohertz. Right? And the DSL will utilize the rest of the frequency band up to 30 megahertz, a huge chunk of frequency, right? And divide it into several parallel channels and transmit data on that so that to fully utilize the capacity of this copper line. However, that because of this larger and larger frequency, there are more and more severe crosstalk or interference between different telephone lines. And that's actually indeed the reason why the original voice traffic only uses a small bandwidth, because at the low frequency, there's no crosstalk. You can operate individually. So when you talk to somebody, you don't hear the voice on the other lines, right? But when you transmit data on a high frequency, they have crosstalks, you have interferences. And this is the major performance bottleneck in the DSL line. So we have to manage the interference. So the current practice is called a static spectrum management, where there is some standard that limits the transmission power of all users, try to protect the other users, try to limit interference, which is static, highly suboptimal, and very conservative. Okay. And since 2002, there's a new wave called dynamic spectrum management, and try to break the regime of the static spectrum management and by optimally and dynamically allocate the transmission power across different frequencies to improve the performance. So what I'm going to talk about today belongs to this class. And on the other side, it also belongs to this Fast Copper project, which is a large project between the Princeton University, Stanford University, and the Free Soul Research in Princeton. And also with collaboration with AT&T, former SBC, a lab, which has now has 60% of the DSL lines in the US by combining bare cells. Right? So the aim of this fast copper is to providing DSL broadband service up to 100 megabps peak rate by joint optimization over frequency, amplitude, space, and time. So this is FAST, fast. Right? And today I'm going to focus on the frequency aspect, which is the spectrum management. So here is the interference channel, interference model in a DSL network. Mathematically, it's actually pretty similar to the multi-channel wireless ad hoc network we just introduced. However, there are some major differences. The first, this channel can be considered to be time invariant because this is a wireline channel. This is not wireless. And the second, because this is wireline, so the crosstalk is heavily topology dependent. So let's explain what this is. Right? This is the telephone central office, which is the transmitter on the downlink transmission. And this is one telephone line. And this is the customer, which is the receiver line, receiver end. And because some customers are in the farther field that just not close enough to the central office, so the central office cannot provide high enough data rate to the customers. So in practice, they employ some small boxes at the roadside called remote terminal. Right? And this is physically farther into the field and closer to the customer's home. So connecting to the customer. So this is another transmitter, this is another customer. Right? And the transmitter on one line generates interference to the other line. And because this interference is topology dependent, it decreases with distance. So the RT transmitter generating strong interference to the customer on the CO line. However, the CO is farther away from the customer on the RT line. So this crosstalk is really small. So this is really a one-way interference in this mixed CO-RT case. And this is the dominant performance bottleneck in the US. In the US, there are a lot of RT deployment. So this is the major problem. And also, due to the characteristics of the copper line, the interference just increased with frequency band. Right? In the low frequency, no interference. And with higher and higher frequency, there are more and more interference. So in the CO-RT case, there is a one-way interference. RT generates excessive interference to CO. CO generates little interference to the RT. And this is also called a near-far problem. And if you can tackle this problem, eventually you can greatly improve the performance of the DSL network. So mathematically, this is the problem we want to solve. That we want to choose the transmission power of each user on all different tones indexed by k, such as to maximize the weighted sum of users' rate in the DSL network, where the rate of the particular user is a summation of the rate across all tones. And a rate achieved on each tone depends on the SR and R, right? Transmission power, interference power, normalized channel gain, background noise. Similar as before, right? And total power constraint, non-negative power constraint. Nothing special here. So the technical difficulty of solving this problem is the following. First, this is a highly non-convex problem in terms of transmission power, and tightly coupled across users due to interference. And because there's no utility involved, then there's no way that we can transform this problem into a convex problem. There's just no way. We have to deal with the non-convexity. Right? And the second, because of this engineering implication, because the telephone lines operate separately, there's no way that they can explicitly exchange information among themselves. Right? So we don't want price information exchange, as in the wireless and ad hoc case. And our purpose is to find distributed and low complexity algorithm with near optimal performance.
Is the mathematical formulation really just the same as the other problem? Like, the other problem was also log of a 1 plus SI and R.
Mm-hmm.
Some of those were with the utilities part, right? So the difference is in the crosstalk or the linking parameters have a different characteristic, and the constraints you would impose on how they will reach a solution, like what information they gather.
Mm-hmm. Right. So the channel gain coefficient have certain characteristics. For example, one-way interference. And the second is that as I said, we don't want to explicit message passing. And the third is that here we have stick with one particular utility function, which is the rate, log 1 plus SNR. Right.
Somehow, like you write words like highly non-convex. Somehow, when you abstract the problem to it's just a set of alphas in the one case,
Mm-hmm.
it's really the same. Right? The other problem is not convex either.
Right. The other problem is not convex either. But under certain utility function, you can make it convex by log change of variables. But here we're stuck with one particular utility function, which is the rate.
The other
So
thing
there's-
he said it was log.
Log
It was all he said is
Oh, this is-
concave and SINR. Now
Right,
he's
right.
saying he's specifically looking at a problem.
So when we say log utility, when it's log of SINR.
Previously it was
Here it's
some
log
other
1
thing.
plus SINR. Yeah.
Right, and also when you say message passing, are you saying that I cannot distribute the prices? Is that what it means? I
No,
cannot-
there's no price exchange. We couldn't do that.
That's
Yeah.
probably the.
Yeah.
But see, isn't this power allocation happening in one of the central offices?
It happens distributively at the central office, the remote terminal, and the multiple remote terminal at each transmitter.
So one practical question, I mean, when a lot of bundles go through a remote RT, whatever, don't all of them get retransmitted again? If that's the case, then there is no one-way interference as such, right? So the question is, for example, all lines leaving from the central office, right, all of them should see symmetric interference.
Good question.
How much are the same?
So in practice, in the real field, so there are, for example, 50 lines going through a cable put on the ground, right? And these lines can come at a different time, can come at different places into the cable and leave at different places. So when you look at a particular, look at these 50 lines, they correspond to 10 companies and 50 homes which located at different places.
So their transmitters were at different distances.
Right. So there's no way of joint optimization by exchanging all the information. Yeah. And that's the important point. So as we said, that we want to do something called a dynamic spectrum management. And here is the partial list of the state-of-the-art of the DSM and the algorithms. The first and the most well-known, one of the first, is total water filling proposed in 2002, which is a distributed algorithm. And later, people proposed a centralized algorithm called optimal spectrum balancing, OSB, and iterative spectrum balancing, ISB. And what we propose is called autonomous spectrum balancing, ASB. So here's a comparison of these 4 algorithms. The iterative water filling is autonomous. There's no information exchange. It's based on game theoretical concept, right? It's a low complexity, linear in the number of users and number of tones, but could be highly suboptimal in the near-far scenario, in the mixed RT-CO case. Later, people proposed OSB algorithm, which is the centralized algorithm collecting all the information. Excuse me. And the optimization involves a joint exhaustive search across all users. So that's why there's exponential complexity in number of users. And the result is asymptotically optimal when the number of tones becomes large, which is the case in DSL network. Right? For example, the VDSL, there are 512 tones. And this is not practical. However, it provides a benchmark for all the other algorithms. So how close to the OSB is a benchmark for your algorithm. Right? And later on, the ISB is an improvement over the OSB. It's a centralized algorithm. And they replaced the joint exhaustive search by iterative search across users. So bring down the complexity of users to quadratic. And it can also achieve near optimal performance. But it is still centralized. What we propose, called ASB, is autonomous algorithm, enjoys same low complexity as the iterative water filling, no explicit message passing. However, it can achieve near optimal performance. So how does that happen, right? So first, let's think about if we want to achieve something close to optimal, what we need. Mathematically, we need the global crosstalk information across all lines, 50 lines in the binder, right? However, that is just not feasible, right? And on the other hand, we know that in the mixed CORT case, which is the performance bottleneck, what we really need? What we really need is to protect the CO line, which is the victim, right? The RT doesn't need protection because the CO is not generating interference to himself, right? And this intuition applies for the multiple CO, multiple RT line case as well. So based on this intuition, we do the following. We propose a concept called the reference line concept, which is the fictitious line representative of typical CO line. So this represents a typical victim in the interference environment. And all the parameters of this fictitious line are fixed. The transmission power, the crosstalk gain, the background noise, they're all fixed based on the field measurement. So you measure the typical service, CO service like, and you put down a fictitious line. So instead of everybody try to maximize the total network rate across all users, it just to consider 2 lines in the network for everybody. One line is himself, the actual line. The other line is the reference line. Okay. And what it tries to do is that it tries to maximize the weighted sum of its own rate and reference line rate. So this brings down an n-user optimization problem to a two-user optimization problem. So this is the mathematical formula, just to repeat what I said. Maximize, try to change your transmission rate over all the carriers to maximize your rate weighted by a parameter and the rate achieved on the reference line. So everything which is tilde, the tilde k, tilde alpha, tilde sigma, are all fixed parameters, known beforehand to everybody, public information. Right? And then everybody solve this problem and iterate through users until convergence.
How do you get that alpha k, alpha tilde, all this?
So these are fixed parameters for the reference line. This is basically represent the typical operation condition of a serial line. And what companies do is that actually this idea, this reference line idea is used in the current practice as well, but not used for dynamic management. Is that you can measure the serial line day by day, month by month, year by year, right? And you accumulate enough data, and you know that typically what kind of crosstalk it is experiencing, what kind of background noise it has, and what kind of power it's operating on. And use that, because this is a timing invariant interference channel. So you can use the fixed parameter for this fictitious line and to achieve good performance. Right? And of course, it changed, depends on the night and day, but it's not changing every second. So this optimization only involves local information because everything here is null. The transmission power is local. The interference from other real lines you can measure locally as well. Right? However, this problem is still non-convex, but can be solved by a dual decomposition. Essentially, the similar argument in the OSB, the duality gap is asymptotically zero when the number of tones is high. Right? And it brings down one subproblem per tone. You can just look at the KKT condition and solve it. So here's the simulation setup. We consider a network with 4 lines, 1 serial line, 3 RT line. And this guy is just a victim, right? It received interference from all these guys. Right? And these guys are okay, right? Especially this guy. There's really no other people can interfere with it. Right? That's right. All 3 guys were interference with, and this guy interference with these 3. Right? So there's a hierarchy interference going this way, right? But not this way around, because this guy is closer to these 3 receivers. And we also assume that the target rate is set to be 2 megabps on the RT2 and RT3, essentially by adapting this parameter W. If the rate is not achieved, we just increase the W until it is achieved. The only trade-off we want to see is what is the achieved rate on this line and what is achieved on this RT1 line. Right? So here's the result. The horizontal.
There's some assumption that everybody's on all the time.
Everybody's on all the time, yes. And in practice, so that's part of the faster cobra project that in the time domain, we consider scheduling, statistical multiplexing, traffic model, so on and so forth. But in the frequency domain, we assume that everybody is on, yes. So the horizontal axis is the RT line, achieved rate in megabps. The vertical axis is the serial line. So this is the Pareto optimal boundary achieved by total water filling, which is the best available technology so far. And everything here is achievable. And this red line is achieved by the OSB algorithm, which is impractical but achieves performs the upper bound. Right? And this is what ASB achieves. ASB enjoys a very low complexity similar as to the water filling, and there's no explicit information exchange. However, it could achieve close to optimal performance as OSB in this mixed CORT case. So this is the summary of the third part that we consider dynamic spectrum management in DSL networks. It proposed the ASB algorithm, which is fully autonomous with low complexity and achieve near optimal performance. And what is not covered here is that we actually propose another algorithm, which is between the ASB and the total water filling, that using high SNR approximation on the reference line, so that this algorithm has even lower complexity, which becomes convex, as faster convergence, but worse performance between the total water filling and ASB. And I also consider asynchronous transmission, where the OFDM channels actually are not orthogonal to each other. They are interference spilling, and the problem becomes more difficult there. Yes?
So it's someone over there going to ask something?
You can go.
So that my sense is that the characteristic of these solutions is that they would identify a subset of users who have have some desirable shared characteristics and give them all the resources. That the solutions would tend to be quite unfair if you operate at some extreme point. And is that true, or is it something I don't understand? Like, for instance, in the wireless case, which is mathematically the same, you would have thought that you end up implementing something that looks like sort of like TV and pick a few selected people. So is that right, or is that?
So it's slightly different here, because essentially, as we can see, that for each algorithm, instead of providing one point, we provide one curve. Right? This curve tells us what's the best you can do, and which point on the curve you operate on depends on the company's objective. For example, if you want to protect a civil service, you can operate somewhere here. And if you want to utilize the RT service, you can operate somewhere here. So it all depends.
So are these the weights that sort of
I
determine
don't
this?
understand what this curve. Do you understand this curve?
No, that's what I was asking. I was going to ask exactly that. So are you just changing the weights? What do each of those points?
That's why I'm changing the weight of the W.
Yeah, so he's weighting it to
Yeah.
make sure your thing goes away. But in essence, I think I agree with you. If you do Pigovian taxation, right? I sort of
That will lead to one solution. Yes, that's right.
The
That's right.
results will lead to solutions where
RT is operating at maximum power. CO just shut off because it's just pointless to use CO. That's right. Yeah.
What about gems?
Yeah.
So can you go back to that curve and just sort of remind everyone what the axes of that curve are?
Oh, okay. So this curve, right? So this is based on this network where there are 4 lines. And we set target lines, the target rate on these 2 lines to be 2 megabps. So this is what we can achieve. So the only freedom we can adjust is the rate achieved on this line and the rate achieved on this line. Right? These are the only 2 unknown results. And this is the plotting. Right? This is the rate achieved on RT line, which is the line here, second line, right? And this is the rate achieved on the CO line. And depending on different weights you achieve, you select your favorite weights for these 2 lines. And you run this algorithm, you can get a particular point. And you change the weight, you can get a curve, right? Pareto optimal curve.
So when you say rate is fixed to 2 megabits per second, it's fixed or it should be greater than 2 megabits per second?
So it's fixed.
Fixed to 2 megabits.
It's fixed. So for these 2 lines that you adjust the W such that it's fixed at 2. If it's greater than 2, you reduce the W such that it's not generating unnecessary interference to other lines. So that's why the comparison of these points are comparable, right? So basically that everything else in the network is fixed.
Can you once again explain the reference line, like in the previous figure?
Sure.
The 3 reference line, 3 RTs and 1 CO, right? And so can you just once again tell like what was the general problem? What were the gains that were needed to be measured in order to solve the optimal problem, and what reduction did you do when you came to
Sure. So here that in order to find the optimal solution, you have to consider the crosstalk between these 4 lines, right? And you have to do a joint optimization, which is impractical in DSL. What ASP do is that everybody, just imagine there's a line between here, which is a reference line. And this guy only optimizes itself and the fictitious reference line. So everybody just sees 2 lines in the network instead of multiple lines. And one is himself, one is another fictitious guy.
So you're not worried about the interference between you're saying the main.
The interference is inexplicitly taken into account here, right? Okay. So you're really, when you calculate the rate, you're still counting the real interference from other users.
Yeah, so
it's just not, you're not maximizing other people's rate as well. That's right.
So in that graph, should RT1 and RT2, that depends on this alpha parameter. Do you have something for what value the alpha bar and p bar with this like that?
So you mean this alpha, right?
Yeah, that curve which you showed, RT1 versus RT2, that were for some specific values of alpha bar and p bar?
Right, that's for specific choice of the p theta, alpha theta, sigma theta, which is from the field measurement. Right.
You can't do any optimization over that too.
That is not the optimization variable. That is essentially, that should mimic a typical CO service. That is from the measurement. It's not what you optimize. Right? So these are fixed.
So somehow in your cartoon, you said, oh, these 2 guys have a required rate of 2 megabits per
Mm-hmm.
Where is that in the problem formulation? Is that somehow you then?
Right, and the problem is that essentially everybody is solving this problem, right? So there are 4 lines.
But the people who have to get 2 megabits per second, is that?
Right.
That's some constraints that aren't written down here.
So here there are W in here, right? So the W is a parameter they can adjust themselves. So they just fix the WN and optimize this and realize that you can achieve 1.5. And they will increase the WN and try to improve its rate until the rate is achieved at 2 megabps.
But the interference depends on the root 1, the RT1, right?
That's right. When everybody changes, when the other 2 changes, then the problem of everybody changes, right? And this is the result as the final result when the 2 actual lines are very happy with their 2 megabps exact.
So at different points, the other 2 lines also have their power change. Is that what you mean? So like if for 2 different points on this curve, right? Since they generate different interference,
That's right.
the other 2 lines, so the other
That's
2
right.
also adjust theirs.
Yes. The other 2 lines always adjust their parameters to achieve 2 megabps.
But is it clear now that the way they adjust their parameters is that there's just one choice of the weights that achieves it, or are there different forms? Somehow it seems like you have a multiple. It's not clear to me that there is a multiplicity of solutions that guarantees those other 2 people their 2 megabits.
So you're talking about the convergence of this whole algorithm, right? Or
Well, I'm just saying, you tell us, you'll just keep adjusting the weights
Mhm.
to make sure users 3 and 4 get 2 megabits.
Right.
And I think, I'm not sure how that works. I don't see. It seems sort of obvious to you. But maybe.
I see. So let me explain more. So first of all, these guys just associate a W for themselves, right? And they do the local optimization, ASP algorithm. And they look at the rate. For example, this guy got a 1.5, this guy got a 1.5. And these 2 will just increase their W and re-optimize. And because the interference change, everybody will re-optimize. And if that doesn't work, they will further increase their W. And if it achieves more than 2 megabps, it will decrease. So assume that there should be a couple of iterations. And until finally, assuming the step size on the adjustment of W is small enough that they will eventually achieve their target rate.
So it seems like you're using the W as kind of a Lagrange multiplier on a rate constraint.
That's right.
Saying what you're doing.
That's right. So there are 2 formulations here. So in this community, there are 2 formulations of this problem. One way is formulated into a weighted rate sum, where the W is fixed. And the other actually is try to maximize a particular user's rate, subject to the rate constraints of everybody else. And if I write out that, it can solve your problem. But this is, originally I hope that this is easier to illustrate, because don't worry about the change in W. But it turns out to maybe that formulation is more illustrative, yes. But these are equivalent, yeah. Okay, actually, so this is already the end of the talk. So basically, in this talk, we talk about 3 applications. All of them are motivated or based on the OFDM technology. And here is the summary slides of the problems and methodologies of each of the algorithm, of each of the problem. So in part 1, motivated by the WIMAX, we consider mixed integer, and convex optimization. And we use integer relaxation tie breaking to solve the optimal solution, or sometimes close optimal solution. And the SRT algorithm proposed is the centralized one, can achieve optimal or near optimal performance, depends on whether tie occur. Enjoys a low complexity and always converges due to the one-dimensional search of the convex function. And in the second scenario, consider a wireless ad hoc network, where the problem could be non-convex or convex, depending on utility functions. And we use Supermodular Games theory to prove the convergence results. The algorithm we propose is distributed one, achieve optimal performance in some case. It's very low complexity and fast convergence. And in the last scenario, we consider DSL Network, which is indeed a non-convex problem. And we use a reference line approximation so that to propose an ASP algorithm, which is a distributed algorithm, achieve near optimal performance, low complexity. And actually, we don't have a good answer of the theoretical convergence of this algorithm, but it always converges in practice. Yes?
Actually, on the second question, why did you, bringing in game theory really helped you prove your result? And is it clear that you could not have done anything with your convex optimization? Because there's a clear relationship between convex optimization problems and certain game theory problems. So I'm not able to understand how going there really helped you solve. For example, if your utility was convex, could you have proved your theorem without having to resort to game theoretic approaches?
So,
I have just a similar
sure.
question.
Sure.
The condition that you talked about, supermodular games, is that like something, can you just show the correspondence to your problem, and like, is that thing necessary for the, I'm not saying you have to go to game theory, but that condition, does it show some kind of inherent property?
So, as you said, if we can convert into a convex optimization problem, there are actually many ways of solving that. However, what we here focus is that we want a fast convergence, where in most techniques, if you want to do the iteration, you involve some step size. But you can see that ADP algorithm, the beauty of it is that there's no step size involved. It always myopic update, so that it converges very fast. And to prove this convergence, at least for me, the supermodular game theory seems to be the perfect tool. So this is only one way of solving, but however, this seems to be a better way than other slower convergence methods that we're comparing with.
So when you mentioned step size convergence, so was it specifically for convex optimization problem? The utility was convex, or was it? Because if you look at non-convex problems, there's probably not much literature out there to work with it. So you
That's
can
right.
go to game theory and borrow some techniques from there.
That's another point, that in a non-convex case, even the current standard techniques with enough, small enough step size doesn't work. But with supermodular game theory, you can at least work with a subset of the problem. Right?
Supermodular games convert, and Nash equilibria exist, irrespective of whether your utility function is convex or not.
That's right.
No
Yeah.
So, but there's no one-to-one relationship with. Can you not formulate those game theory problems as, like, for example, maximize such and such non-convex function subject to these?
I think that's what he's done then.
Yeah,
In this case.
That's right.
Convex,
Yeah.
I don't think you need to go there. But
Because the direction of arrows that you had in your figure, did it have a real meaning that you can go one way, you can't go the other way?
The arrow basically represents that the ADP algorithm and the supermodular game are supporting tools for solving the optimization problem. That's the arrow means. And there's a directional arrow, which means these two are somehow equivalent. Okay. So this is the end of my slot. Thanks all for your patience. I think this is well beyond 1 hour. And I'm open to any suggestions and collaborations. Thanks a lot.